If you cannot hear me clearly, please let me know. So in the last class, we have discussed about the electric field concepts. So we have we have discussed mainly regarding the Gaussian law and how we can define using equations. We have discussed about electric field and electric flux density concepts. And we have discussed about the relationship between those electric flux and electric flux density. So basically, with the Gaussian law, uh, we are uh, kind of covering the required concepts that we need to understand how an electric field is created and how an electric field is behaving in a certain closed surface. So in Gaussian law, we understood that when we have a certain closed surface and when we have a certain charge inside it, uh, the electric field that is generated produces electric field lines which travel from the positive charge towards the outer surface, outer space of the surface. So in that case, we can determine the uh, amount of electric flux that is generated based on the charge that is inside. So then we also learned about the electric field and electric flux density. So we can relate those D equals epsilon naught E, where E is the electric field, uh, epsilon naught is the uh, permittivity of the free space. And electric flux density is D. So electric flux density is denoted by the letter capital D. So whenever you see the capital letter D, you need to keep in mind that it represents the electric flux density. So electric flux density is defined as the amount of electric flux that travel through a unit surface area. So amount of electric flux per unit area. Next, we understood the relationship between. I think these both are same. These questions are same. So we define this relationship regarding electric field and electric flux density. So with that, we concluded basically uh, the electric field and the electric flux density concepts. So next we have uh, this simulation that we can look into, that we can use to understand a little more about electric field that is generated in a space with electric simulation. Using these simulations, you can understand how the electric field is generated in a certain region based on the charges that are spreaded in the region. So once we the electric field is basically depending on the amount of charges that are available in the space. So based on the distribution of the charges, the electric field that is generated in that region also varies. So we can get some idea about how we can uh, code this. So I hope it is visible to you. So if you have any questions, you can ask. And you have using, so I have given the OTP code in the chat. Right, so you only have time until first 30 minutes, so you need to mark your attendance during that time. Otherwise, your attendance will not be marked. So yes, so permittivity is depending on the type of material that the uh, the field is available. So so permittivity parameter depends on the material of the space, or the material that is in the space. So in this in the previous equation, I mentioned to you about the uh, free space permittivity epsilon naught. So this is only valid for the free space. So permittivity is a general term that you can use for any kind of a material. So permittivity we can define as the relative permittivity into free space permittivity. So depending on the material uh, that through which our electric field is generated, we need to consider the relative permittivity of that material, and we need to put that value in here in order to get the total, I mean, the permittivity value in that medium. So the relative permittivity coefficient needs to be added where we consider other materials and like not the free space, right? Epsilon naught is used only if we consider free space, right? So in the like in my explanations, I always use this epsilon naught. So in those cases, you need to keep that in mind that I'm considering the free space behavior. So that is what you need to keep in mind. So this is the most simplest version. If you want the if you want to add this equation to any other medium or material, you can add epsilon r into epsilon naught e as the expression uh, that relates the relationship between electric field and the electric flux density. So if you are clear about that, please let me. So I hope it's clear to you. If you are not clear, please let me know. So in this simulation that I mentioned, we can simulate like an area with a lot of charges spreaded, and the spreading of the charges we can determine using the simulation platform. So I will share this code with you in the LMS. So this code basically uh, tells us how we can define a certain area first, which is done by this X list, Y list, and so on. So we first create an area that we consider, and then we define some parameters to the simulation, and then we measure certain like parameters, such as like in here the parameter r means like the different distance difference between two charges. So that parameter is required for us to find the electric field strength on a certain charge due to another charge. So likewise, we can actually define the magnitude of the electric field and using this equation. And the electric field magnitude and electric field direction can be determined using the direction can be determined using this angle theta. So after that, the components along x and y directions can be defined using ex and ey uh, parameters. Actually, they are variables. So this code actually allows us to define the charges that we want to spread in the area, and depending on the magnitude of the charges, we can get the uh, output of our electric field distribution. So once we actually go to this final output, you can see a figure. So based on the initial charges that we have placed in the area that we have defined, the total force that is acting on each point of the space is given by the arrows in this figure. The if the charges are very close to the observing point, the force is very large. If the charges are that to the observing point is large, then the force experience at that point is low, because the observing point is very far away from the internet from the charge. We can define the charges location in this space using the code, and based on the location of the charges, the effect of those charges in these points vary, and the effect is given by this strength of the force. So we can do it for any kind of charge distribution. So I will show you how I have done uh, one simulation by equal magnitude and opposite opposite type. That means like I have kept two charges, one positive charge and one negative charge. So in this simulation, in this list charges, we can define the charge that we want to place and the location that we want to place it. So if we place a charge dq, the dq charge I define using the parameter in here. So that can be defined by you by any kind of a method that you prefer. So dq is a certain magnitude, some kind of a it has a some magnitude, and dq is the magnitude of the charge, and the location of the charge is given by the x and y. So x coordinate and y coordinate define the location of the charge. So I first keep the charge in location x that I define. X is defined as minus 0.1, and y is defined by me as minus 1. So there's one charge in minus 0.1 and minus 1. Another charge with the same magnitude but in uh, different type. That means this is negative charge. This is negative charge, and this negative charge is kept in the minus 0.1 point itself, but the y point is positive 1. So based on that, I run this simulation, and I keep therefore therefore there are two charges, right? One in minus 1 point, one in plus 1 point. right? So we consider the same x coordinate. In the same x coordinate, we keep two charges in two different places in the y-axis. So y equals 1 and y equals minus 1. So once we do that, we can see the electric field pattern changing like this, and the electric field charges are, I mean, shown using the arrows. So since we have kept the positive charge in the minus 1 point, the electric field are moving outward from that charge. And since the top charge is a minus charge, negative charge, the electric field is ending at that charge. So because of that, the overall electric field distribution is shown to start from the positive charge and to end in the negative charge, right? So this behavior is something we have discussed. So we have discussed about the dipole electric field, the electric field of a dipole. So this is the electric field of a dipole. So we can simulate such kind of uh, uh, charges and distribution of charges. We can distribute charges in the way we want, and then we can observe the electric field that is generated in the space, right, due to all the other charges available in the space. So the total sum electric field distribution we can observe using this simulation tool easily. So I will provide you with the raw sample code. You can adjust the sample code and I observe the different electric field distributions that can occur due to the electric charges that you place in the space. So that is basically related to the simulation. So I think you might need to get familiar with these kind of platforms. One thing is that it is beneficial for you to verify the concepts that we learn mathematically in the class. So learning concepts mathematically might not be enough. So you might need to understand how to simulate it in a certain computer and get the outputs from a computer, because in the current world we are working with computers, not with the papers only. We do use the papers, but we need to go beyond that. We need to implement in computers. So once we implement in computers, we can replicate it anywhere, and then we can use it for different applications. So therefore you need to get familiar with these platforms. So so it's up to you to get familiar with these simulations, and if you have any questions you can let me know, right? So this code is basically written using Python programming language. So if you are not familiar with it, you can learn it using the internet. Right now we have chat GPT as well. So that kind of tools are really useful for you to learn a programming language. You just need to understand necessary instructions on how to understand the codes and how to write your own code. So actually, the Python codes will not be evaluated in the exam. Small assignment that that you can do using this simulation platform. So with that, I think we have covered the and talk about the magnetic field and the magnetomotive force. So so today we will be starting about the magnetic field and the magnetomotive force. So this is a new concepts related to Coulomb's law. Gauss's law. So those laws were basically used to find the electric field at a certain point in space due to a certain electric charge available in the space. So we have learned that not only we have we have discussed about a single charge, but we have discussed about multiple charge and how those multiple charges can affect the electric field at a certain point in the space. So now we are going to go towards the Ampere's law and Faraday's law and Lenz's law, where those laws are proposing laws related to magnetic fields. So these magnetic fields and those electric field concepts are used by us at the end to understand the electromagnetic uh, behavior and the electromagnetic wave generation. So magnetic fields uh, are basically uh, magnetic field refers to a region where we experience a certain magnetic force. Uh, so uh, uh, so we have seen magnetic force in the space due to magnetics when we were doing science experiments uh, in our elementary or secondary classes. We were able to see that once we keep a certain magnet in a certain region, that region can experience a magnetic force at each point around that magnet. So magnetic fields can be generated basically using two methods. We can generate using permanent magnets. Permanent magnets generate magnetic fields, and those permanent magnets are like from their own nature they generate magnetic fields. So there are materials like iron, cobalt, nickel, which produce the magnetic field around it. So that is something that happens naturally, and those items are able to produce a magnetic field. So once we keep such permanent magnets in a area where we have, for example, graphite powder, then we can see the magnetic field lines that are generated around the permanent magnet due to the magnetic field. So we can see the metal powder forming certain lines from the north pole towards the south pole. So the force that is generated around the permanent magnet causes these metal fillings to form in that certain manner. So another thing is we can also create magnetic fields using electric currents, right? So I think that is one of the major discoveries in the field of science. So although we are able to find a magnetic field around the permanent magnets are not available all the time or in every place. I mean, it is very hard to find the natural permanent magnet for our applications. So rather than going for the permanent magnets, we have this option of using electric currents to produce magnetic fields. So we can use electric current basically, and we can see a magnetic field getting generated around that current carrying conductors. So we are going to be learning about that concepts in this class. So this also enables us to understand how the electromagnetic wave is generated using antennas, right? So you know that antennas are consisting of a metal rod that has that carries electric current. So the metal rod that carries the electric current is able to form electric field, and then because of the electric field it can produce magnetic field around that uh, antenna. So if we take an antenna, for example, this antenna will carry current. So we will provide some current from a voltage supply that we have, and then because of the current that is flowing in this conductor, the current will produce a magnetic field around this conductor. So the current field will also will also have another effect. The magnetic field that is generated will have another effect. That field will generate an electric field. So because of that, the electric field and magnetic field will be generated in a it will along the space. So the electric field will be generated due to the magnetic field, and due to the electric field, again magnetic field will be generated. Event will happen in like a chain, and that chain will allow us to propagate a certain signal from the antenna location to another location. That is what is magnetic field. So that is that is something we are going to learn in the next classes. However, now forming a magnetic field from an electric current is the basis for that understanding. Like not normally in all magnets we have north pole and south pole, right? Have you seen like a magnetic monopole? Have you seen a magnet with only one pole, only north pole or south pole? Have you seen a magnet with only one pole? Magnetic monopoles, that is. So actually we don't have magnetic monopoles as of now in existence in the world. So all the time north and south poles exist together, and like we do not have the existence of one pole only. So we have both north pole and south pole working together to form the magnetic field, right? So we do not have magnetic monopoles as of now. However, some scientists are saying that there could be some magnetic monopoles existing in in some situations due to some reasons. However, that had not been discovered or proven up until now. However, uh, therefore, I mean, we can understand that we need both north pole and south pole for a magnet to function in the way such that the magnetic field is generated. So so as you think, so what happens once we bring a magnet with north pole and south pole to another magnet with again a north pole and south pole? If we bring a north pole and south pole magnet, a bar magnet like this, to another bar magnet with north pole and south pole in this manner, what is going to happen? Are they going to repel or attract? So like poles repel, right? So like poles repel. So therefore, once we bring north pole to a north pole, the magnets will repel. If we bring opposite poles together, the magnets will attract. So unlike poles will attract. So that is the basic rule for the magnetic poles. So like poles will repel, and same poles will, unlike or opposite poles will attract. And so we were discussing about the bar magnet. So bar magnet we can draw like this, right? So we have the north and south pole. So magnetic field starts to flow from north to south or south to north. How do you normally draw it? So you start by north or south, the magnetic field. Yeah. So normally, yeah, we draw it from north to south, right? We draw it like north to south in this manner. We can actually draw it in a more clear manner, like they should be symmetrical actually. So you can draw it. You can draw it when you want. So in both sides we have the same like distribution of the magnetic field, and the magnetic field lines will be symmetrical along in both sides. So after that, what is the direction of the magnetic field inside the magnet? We have the lines moving from north to south. Magnetic field are continuous, right? So therefore, how does the magnetic field travel? Magnetic field lines are continuous, right? So magnetic field lines are like it doesn't stop at south. South, it stops at north, right? It starts at north and it stops at north. So therefore, the lines will be continued from south to north. The North Pole, which came to the South Pole, will go from South Pole to the North Pole, and will continuously will travel like that. Right? So because of that, magnetic field lines are actually continuous lines. So the magnetic dipole will have magnetic lines like this, and the magnetic lines will be continuous. From it will start from North Pole and it will end at the North Pole. So this is different from the electric field lines. Electric field lines, we had the positive charges, and the positive charges were ending at the negative charges. So we had the electric field lines starting from the positive charge and ending at the negative charge. So like this. However, there was no intermediate line between negative charges and positive charges. So having we were having lines starting from positive and ending at negative. However, in the magnetic field, we have lines starting from north pole and ending again at the north pole. So inside the magnet also we have magnetic field lines traveling from south pole to the north pole. I hope it is clear to you. If you have any questions, you can ask. So this is a figure which shows some of the main like important parameters that are regarding magnetic fields and magnetic field lines. So if we have a bar magnet with the north pole and south pole, the magnetic field lines will generate to start from the north pole and it will end at the south pole. And in between also the lines will be there from south to north. So normally we don't mention that in the magnet itself. So however you can know it. So in the electric field classes we learned about electric field strength, electric field flux, and electric flux density. In magnetic field also we have that are going across a certain surface, magnetic flux density, which defines the amount of magnetic field lines across a unique surface. So once we have electric field lines like this, we can define these lines as magnetic field lines, and those magnetic field lines can denote the magnetic field that that is generated by the magnet, and the amount of magnetic field force that you experience in a certain point uh, we call as the magnetic field strength, right? So we will try to electric field, sorry, magnetic field, magnetic field we define as the amount of magnetic force experienced by a specific point in the region. Right? So a magnetic field is a force that is experienced by a certain point in the region. So we talked about the bar magnet. So if we take a certain point in the space around that magnet, whatever the magnetic field that is in this point is defined as the amount of force that is experienced by this object due to this magnet. We call as the magnetic field. Magnetic flux is the total amount of across a certain surface. So we can define a certain surface, and we can uh, compute the amount of magnetic field lines across that surface. So surface, it could be open surface, could be a rectangular open surface like a plane. So we can keep magnetic inside these surfaces, and then we can count the amount of magnetic field lines that are coming out of the surface. So depending on the surface that we consider, the magnetic flux that is coming out from the surface will vary. So this rectangular one is a surface. So this is open surface, right? So if we take the like another view of the rectangular surface like this, actually, if we have in this manner the plane, then the magnetic flux lines can go through this surface. So the amount of magnetic flux lines that go through this surface is known as the magnetic flux. So so the total amount of magnetic flux across the total surface is known as the magnetic flux. So if we have a closed surface, again we have another like another thing that we need to consider. So uh, anyway, we will discuss more about the magnetic flux through a closed surface in the next parts of this lecture. So magnetic flux is the total amount of magnetic field lines that is going through a surface. Magnetic flux density is the total amount of magnetic field lines that go through a certain unit area. So the amount of magnetic field lines per unit area. So magnetic flux density gives us the the strength of the magnetic field per unit area. So magnetic flux density is defined like in an equation in this manner. So magnetic flux density is denoted by capital D, and it is related to mu naught into H, right? So this is known as the magnetic field strength. We can just call it as magnetic field, and this is known as the free space permeability. So permeability of the free space. This is the amount. This is the magnetic flux density. Right. So magnetic flux density can be defined as mu naught into H. So mu naught is the permeability of the free space. As I said before, if you want to apply this relationship onto another medium, you can multiply this mu naught by mu r. That means relative permeability. This is the equation that you can use for any medium with the relative permeability of mu r, right? So this is relative permeability. So the word permeability is used to define like how much of a ability does the medium has to generate a magnetic field. So mu is the ability of a certain medium to generate of a medium or a material to generate a magnetic field. So we learned something similar in the electric field, which is epsilon. Right? So permittivity. This is the ability of the medium to generate electric fields. So there's some other deep definitions. So basically, the ability to generate an electric field uh, can be used to represent this is used to is defined by this parameter, and it is known as permittivity. So those two terms you might need to remember. So this is permittivity, this is permeability. So for magnetism, we use permeability parameter. For electric fields, you use the permittivity parameter. Sorry, E. So as you see, these two relationships are almost, I mean, similar. However, instead of magnetic flux density, in here we have electric flux density. This is electric flux density. And instead of magnetic field, in here we have electric field. Instead of mu naught, we have here epsilon naught. So they are both related, and they are given in the kind of the same manner, in a same similar pattern, such that it is actually so this magnetic flux density is defined in terms of magnetic field using this equation. So we can use this equation for further for the calculations. So this is an important equation. So those are the parameters that are important for magnetic fields. So now we will consider about the magnetic field, those the SI units of those parameters. Right, so once we are actually seeing the parameters, now we have learned about the parameter B, H, and another parameter is also there, which is flux, magnetic flux. Let's take that parameter as this symbol phi. Right. So for electric field, I think I defined in the class this D, uh, DE, and phi. So for electric field, I defined the flux as phi using phi symbol. So for magnetic field, we will define the magnetic flux using this capital phi symbol. So for those three parameters, we need to define the SI units. So basically, the SI units of these parameters you can also find. We can derive those parameters using the equations that we know. So an equation that we require for understanding the unit of the magnetic field is the equation for the magnetomotive force. Right. So we need to first use the magnetomotive force equation to find the unit of the uh, B field, and then we can define its units. Right, so we will do that next. For a magnetic field, the SI unit is amperes per meters. For the flux, the SI unit is Webers. So you can also Google and find out the SI units of these parameters. So the reason is there could be different SI units for a certain parameter depending on the equation that we use to find its unit. So, however, the SI unit could be something different than the one we derive. So, you can refer from the internet as well. So, as according to my data, so the units of flux, magnetic flux, will be Webers. Unit of the magnetic field will be amperes per meters. Unit of B field will also will be Tesla. So we will get to that when we discuss the magnetomotive force. Right. So magnetomotive force we will discuss a little bit as well. So the magnetomotive force is defined using this equation, right? So V cross B, right? So in here, so this F means the force, right? The magnetomotive force. The Q denotes the charge that we consider at a certain time, and we denote the velocity of the charge. And then B denotes the magnetic field. Magnetic field in flux density, right? Magnetic flux density as we defined below previously. So this equation we can expand further using cross product definition, right? So can you write? Can you tell me the expanded version of this equation? V cross B. How can we write V cross B in terms of the cross product definition? So yes, we can write that V cross B is equal to V magnitude, B magnitude, sine theta, and what else? We need something else, right? We need a direction to this, a unit vector, which shows the direction of the output vector, which is given by the cross product between these two vectors. If we have the velocity of a charge in a certain direction and the magnetic field in another direction, then once we take the cross product of these two vectors, the output vector will be in a certain direction. And the unit vector along that direction we need to define as n hat. So the complete expression direction of the cross product of the two vectors, velocity vector and the magnetic field vector. So because of that, we need to define that this is a vector. So the force is by the unit vector. So so basically we can define the force like this. And we when we want to find the units of the B, is we can take B as the subject and we can divide the force with the other parameters, right? So we can neglect having the units of this one. I can write Newton, coulombs, meters per second, right? So basically other two we will not consider for the for the units, right? Unit vector does not have a unit, and sine theta also does not have a unit. So Newton seconds per coulomb meters. So this one we define as Tesla. So this is the SI unit of the magnetic field. Do you have any questions? Next we in the next class. So today actually we learned about mainly the electric field. Uh, we learned about the electric field uh, and about the electric field generated by multiple charges. So we learned how the electric field distribution of a dipole is represented using that simulation platform. And so simulations of electric fields we have done in a region. Next, we started talking about the magnetic fields. So we started talking about the magnetic field, magnetic field, its definition, and how magnetic fields are generated. So magnetic fields are available as permanent magnets, or magnetic fields are generated using electric currents. So magnetic fields can be generated using electric currents. So because of that, we are able to now generate magnetic fields artificially using electric currents. So we do not need permanent magnets specifically to generate a magnetic field. So we discussed about the magnetic field of a magnetic dipole. We discussed that it should be continuous, and that the electric field or magnetic field lines start from North Pole and end in North Pole. So the magnetic field lines will be symmetric around its axis, and we can see that the magnetic field lines are continuous. Uh, so then we discussed a little bit about the parameters that define a magnetic field. So magnetic field related parameters are like magnetic flux, which we can define using this capital phi symbol, and magnetic flux density, which we define using capital B letter. And then we said that capital B is related to the magnetic field, which we can give as using capital H, using this relationship. So this relationship can be used for a free space. If we want to apply it for a medium, we can add the relative permeability coefficient and add using this relationship. So this is the permeability coefficient. And we also talked about the units of magnetic flux density. So in order for us to find the units of magnetic flux density, we need to consider the equation of the magnetomotive force. So magnetomotive force is defined by F equals Q V cross B. We can expand it further by saying Q V magnitude B magnitude sine theta and unit vector n hat. So by taking the B as a subject, we were able to say that the units of the magnetic field is Newton seconds per coulomb meters, which we call as Tesla. So in the next class, we are going to discuss about the the behavior of the magnetic field inside a certain closed surface, and how the magnetic flux is traveling across the surface, and whether it is traveling across the surface or not. So we are going to be talking about the surface, the total total flux which is going across the surface in the next class, and how those things matter in the electromagnetic wave generation. So that's about it for today's class. So if you have any questions, you can let me know. So for lateral entry students, I will be conducting the class at 7 p.m. So if you want to join, you can join that also. So if you have any questions, you can email me, and most probably I will have this class on in online mode in the next week. Is that okay with you? If it is okay with you, please let me know. I will ask from your batch representative as well regarding that, because currently I'm having some problems in attending the class in the physical mode. So I will prefer to do the online one. However, you can let me know during this week whether you're okay with it or not. I will send a message in the but let me know about that as well. So if you have any questions, please email me, or you can send me a message in the WhatsApp group chat. So I will end the class now.